In this video, we will focus on the dynamics of excavators, which involves the forces, torques, inertia, and load interactions that occur during digging operations. We will explore how hydraulic pressure is converted into digging force, how soil resistance affects machine performance, how inertial loads influence motion, and how engineers ensure that the excavator remains stable under heavy loads. To truly understand excavator performance, we must start with the most fundamental question: where does the digging force of an excavator actually come from? Excavator dynamics deals with the forces, torques, inertia, and energy interactions that occur during excavation operations. Every digging cycle involves a complex combination of hydraulic force generation, soil resistance, structural loading, and machine stability. When the bucket penetrates the ground, hydraulic cylinders generate large forces which are transmitted through the linkage system to break soil and lift material. At the same time, the excavator structure must withstand dynamic loads while maintaining stability on the ground. This interaction between hydraulics, soil mechanics, and structural mechanics forms the core of excavator dynamics. The primary source of force in an excavator comes from its hydraulic system, which converts engine power into powerful mechanical motion. In a typical hydraulic excavator, the diesel engine acts as the primary power source and drives one or more hydraulic pumps. The engine crank shaft usually rotates at high speeds, typically around 1800 to 2200 RPM, while hydraulic pumps are designed to operate efficiently at a specific speed range. Therefore, the pumps are often connected to the engine through a pump drive gearbox, which reduces the engine speed to the required pump operating speed. This gearbox also helps transmit torque smoothly from the engine to the pumps and allows multiple pumps to be driven from a single engine output. These pumps draw hydraulic oil from the reservoir and deliver it into the hydraulic circuit. As the pump rotates, it creates a low-pressure zone at the inlet, allowing oil to be drawn from the tank. The pump then forces the fluid out through the outlet by converting mechanical energy from the prime mover into hydraulic energy. This process generates continuous flow within the hydraulic circuit, supplying pressurized fluid to the system components for performing mechanical work. In modern excavators, the hydraulic system typically operates at pressures ranging from 300 to 350 bar, depending on the machine size and design. This high-pressure oil is then routed through the main control valve and hydraulic lines to different actuators in the machine. The control valves regulate the direction and amount of oil flow based on the operator's joystick input. From there, the pressurized oil reaches the hydraulic cylinders, which convert the hydraulic energy into linear motion. These cylinders are primarily responsible for actuating the boom, arm, and bucket, enabling the excavator to perform digging, lifting, and dumping operations. When pressurized oil enters the cylinder chamber, it pushes against the piston surface, creating a linear force that extends or retracts the piston rod. This relationship is described by a fundamental hydraulic equation. The force produced by a cylinder is equal to the hydraulic pressure multiplied by the piston area. The boom cylinder raises and lowers the entire front attachment, the arm cylinder controls the extension and retraction of the stick, and the bucket cylinder rotates the bucket during digging and dumping operations. Together, these cylinders coordinate to produce the powerful digging and lifting actions of the excavator. In modern excavators, hydraulic pressures typically range between 300 and 350 bar, which allows cylinders to produce forces of several hundred kilonewtons. However, the force at the bucket is not simply equal to the cylinder force. Instead, the excavator linkage acts as a mechanical transmission system that amplifies or reduces the applied force depending on the geometry of the mechanism. As the bucket moves through its digging path, the mechanical advantage changes continuously, which means the effective digging force also changes dynamically during the excavation cycle. This is why excavators are designed so that maximum force occurs near the initial bucket penetration stage, where soil resistance is highest. Once the bucket contacts the ground, it must overcome several types of soil resistance forces. The most significant of these is cutting resistance, which is the force required to break and separate soil particles as the bucket penetrates the ground. In addition to this, the bucket also experiences frictional resistance as soil slides along the inner surfaces of the bucket. Another important component is the passive earth pressure exerted by the surrounding soil mass, which pushes back against the bucket during penetration. The magnitude of these resistance forces depends greatly on the type and condition of the soil. loose sand generally offers lower resistance, allowing the bucket to penetrate more easily. In contrast, cohesive soils, such as clay, provide higher resistance due to the bonding between soil particles. Hard or compacted materials, including rock, create extremely high resistance and therefore require reinforced buckets, stronger teeth, and higher hydraulic forces to excavate effectively. From a dynamics perspective, soil resistance acts as an external load that the excavator must overcome using hydraulic force and the mechanical advantage of its linkage system. This interaction is highly dynamic because soil conditions can change continuously during the digging process. As the bucket penetrates deeper and gradually fills with material, the load acting on the boom and arm increases, causing the forces within the excavator structure and hydraulic system to vary throughout the digging cycle. These resistance forces can be approximated using a simplified soil mechanics relationship formula. Here, R represents the total soil resistance force, C is the soil cohesion, A is the cutting area of the bucket edge interacting with the soil, W is the weight of the soil being displaced, and psi is the internal friction angle of the soil. The magnitude of digging resistance varies significantly depending on the soil type and its mechanical properties. For example, loose sand typically offers a resistance in the range of 50 to 100 kN, while clay soils may require 100 to 300 kN of force due to their cohesive nature. In more demanding conditions, such as hard rock or highly compacted ground, the resistance offered by the material can be extremely high. In such cases, the required digging force can exceed 500 kN. To handle these high loads, excavators designed for these applications are equipped with reinforced rock buckets, heavy-duty bucket teeth, stronger boom and arm structures, and high-pressure hydraulic systems capable of generating greater digging forces. For example, a 20-ton class excavator typically produces a bucket breakout force in the range of 140 to 180 kN, which is suitable for general soil excavation and clay. Larger machines, such as 40-50-ton excavators, can generate 300 to 400 kN of digging force and are commonly used in quarrying or heavy earth moving. In extreme applications, like mining and rock excavation, very large excavators may produce more than 500 kN of bucket force, allowing them to break compacted rock layers and hard geological formations. In addition to external soil forces, excavators must also deal with inertial forces that arise from motion. According to Newton's second law, whenever a mass accelerates, a force is required to produce that acceleration. When the excavator operator rapidly moves the boom, arm, or bucket, the mass of these components generates inertial loads. These inertial forces become even more significant when the bucket is filled with soil. For example, a loaded bucket may weigh more than 1,000 kilograms. If the excavator accelerates this mass during lifting or swinging, additional forces are introduced into the hydraulic system and structural components. These dynamic loads can cause pressure fluctuations in the hydraulic circuit because the hydraulic system must quickly respond to changes in load and motion. When the boom, arm, or bucket accelerates or decelerates, the hydraulic cylinders require rapid changes in oil flow and pressure. This can create temporary pressure spikes or variations within the hydraulic lines and valves. At the same time, these changing forces are transmitted through the excavator's structure, increasing the stresses experienced by the boom, arm, and their connecting joints. Over repeated operating cycles, such fluctuating stresses can contribute to structural fatigue if the components are not properly designed to withstand dynamic loading. In large mining excavators, the mass of moving components can exceed several tons, meaning that inertial effects play a critical role in machine design. Engineers must carefully analyze these forces to ensure that the excavator operates smoothly and that its structural components can withstand repeated loading over long periods of use. If these dynamic loads are not properly considered during design, they can lead to excessive vibrations, unstable machine behavior, or gradual material fatigue. Therefore, engineers evaluate these forces through simulations, testing, and structural analysis to ensure that the excavator can operate reliably while maintaining durability and safety throughout its service life. Another important aspect of excavator dynamics is the swing motion of the upper structure, which plays a crucial role in the machine's productivity and operational efficiency. During a typical digging cycle, the excavator repeatedly rotates its upper structure between the digging point and the dumping location. This motion is performed many times during operation and involves rotating the entire upper assembly of the machine. The rotating mass includes major components such as the engine, hydraulic pumps, fuel tank, counterweight, operator cabin, boom, arm, bucket, and the excavated material inside the bucket. Because this rotating assembly is extremely heavy, the system possesses significant rotational inertia, meaning that it resists changes in its rotational motion. When the excavator begins to swing, the swing motor must generate sufficient torque to accelerate this large mass. Similarly, when the swing motion needs to stop or change direction, the system must decelerate the rotating mass, which again generates substantial dynamic forces. These forces are transmitted through the swing drive system, which typically consists of a hydraulic swing motor connected to a planetary gearbox that drives the slew ring bearing mounted between the upper structure and the undercarriage. The slew bearing is a critical structural component that supports the entire weight of the upper structure, while allowing it to rotate smoothly. During swing acceleration and deceleration, large loads are transferred through this bearing, as well as through the swing gearbox. If the swing motion were to start, or stop abruptly, these loads could create severe shock forces that may damage mechanical components or cause excessive vibration in the machine. To control these dynamic effects, modern excavators incorporate several swing control mechanisms. Hydraulic systems include swing braking valves and anti-shock valves that regulate the flow of hydraulic oil to the swing motor, allowing the rotation to accelerate and decelerate gradually. Hydraulic cushioning is also used to absorb sudden pressure changes within the swing circuit. In addition, many modern excavators use electronic control systems that precisely regulate hydraulic flow based on operator input and machine conditions. These technologies ensure smooth and controlled swing motion, improving operator comfort while protecting critical components such as the slew bearing, swing gearbox, and structural frame from excessive dynamic stress. Excavator dynamics also includes the detailed study of machine stability, which is critical for safe and efficient operation. During excavation, the excavator frequently lifts soil or rock while the bucket is positioned at a large horizontal reach from the machine's center of rotation. This creates a tipping moment around the edge of the undercarriage or the track contact line with the ground. The magnitude of this tipping moment depends primarily on the weight of the lifted material and the horizontal distance between the bucket load and the tipping axis. From a mechanical perspective, the tipping moment can be expressed as the product of the load and its horizontal distance from the pivot point. If this overturning moment becomes larger than the resisting moment generated by the weight of the excavator itself, the machine may begin to lift one side of the tracks or even tip over. The resisting moment is mainly produced by the machine's own mass, the counterweight, and the position of the center of gravity relative to the tipping axis. To ensure stability, excavators are equipped with large counterweights mounted at the rear of the upper structure. These counterweights are carefully sized and positioned during the design phase to shift the machine's center of gravity toward the rear, thereby increasing the resisting moment against forward tipping when the boom and bucket are extended. The counterweight effectively balances the mass of the boom, arm, bucket, and payload during digging and lifting operations. Another important factor contributing to excavator stability is the undercarriage design, particularly in crawler excavators. The wide track base and long track length create a large support polygon on the ground. This increases the machine's resistance to tipping by distributing loads over a broader contact area. The track structure also lowers the overall center of gravity of the machine, further improving stability during operation on uneven or sloped terrain. However, excavator stability is not governed only by static conditions. In real working environments, the machine is constantly subjected to dynamic effects. For example, when the excavator swings a loaded bucket from the digging point to the dumping location, the rotating mass generates centrifugal forces and inertial loads. These dynamic forces can temporarily shift the effective center of gravity and increase the tipping moment acting on the machine. Similarly, rapid acceleration or deceleration of the boom, arm, or swing system can introduce additional dynamic loads that influence stability. Because of these factors, engineers must analyze excavator stability using both static and dynamic stability criteria. Advanced excavator design involves detailed engineering analysis to ensure that the machine remains stable and performs reliably under all operating conditions. engineers often use multi-body dynamic simulations to model the excavator as a system of interconnected rigid bodies, such as the boom, arm, bucket, upper structure, and undercarriage. These simulations allow engineers to study how forces, motions, and inertial effects interact during real digging cycles. By simulating different movements, such as lifting, crowding, and swinging, the dynamic loads acting on the machine can be predicted with high accuracy. In addition to simulations, engineers perform load case studies that represent various extreme or critical working conditions the excavator may encounter. These load cases typically include scenarios such as maximum digging reach, maximum bucket load, rapid swing acceleration or deceleration, lifting heavy loads close to the tipping limit, and operating on uneven or sloped terrain. Each scenario is analyzed to understand how forces are distributed through the machine structure and how they affect stability and component stresses. Another important part of this analysis is the calculation of the stability margin, which indicates how close the excavator is to its tipping limit. The stability margin is determined by comparing the resisting moment generated by the machine's weight and counterweight with the overturning moment created by the bucket load and its horizontal distance from the tipping axis. By evaluating these margins under various load cases, engineers can ensure that the excavator maintains adequate safety factors and remains stable even under demanding operating conditions. Excavators operate in repetitive duty cycles, and each cycle subjects the machine's structural components to continuously varying loads. A typical digging cycle includes bucket penetration into the soil, crowding of the arm, lifting of the loaded bucket, swinging toward the dump location, dumping the material, and returning to the digging position. During each of these stages, forces acting on the boom, arm, bucket linkage, and attachment joints change in both magnitude and direction. As a result, structural members experience fluctuating stresses rather than constant loads. These stress fluctuations occur because the excavator structure must simultaneously resist several forces, including hydraulic cylinder forces, soil resistance forces, gravitational loads from the bucket and payload, and inertial forces generated by motion. When the bucket penetrates the ground, large compressive and bending stresses develop in the boom and arm. As the bucket fills with soil and is lifted, the load increases further, producing additional bending moments and shear forces. When the machine swings or stops suddenly, inertial loads introduce dynamic stress variations in the structure. Over thousands or even millions of operating cycles, these repeated stress variations can lead to fatigue failure. Fatigue occurs when a material is subjected to cyclic loading that causes microscopic cracks to initiate at stress concentration points, such as weld toes, bolt holes, or abrupt geometry changes. Once initiated, these cracks gradually propagate with each loading cycle until they eventually lead to structural failure. For excavators operating in demanding environments such as mining or heavy construction, fatigue resistance is therefore a critical design consideration. To prevent such failures, engineers perform detailed structural dynamic and fatigue analysis during the machine design phase. One of the most important tools used in this process is finite element analysis, FEA. In this method, the excavator structure is divided into thousands or even millions of small elements, allowing engineers to simulate how stresses and strains are distributed throughout the boom, arm, and other structural components under different loading conditions. These simulations help identify areas where stress concentrations occur and where reinforcement may be required. In addition to static stress analysis, engineers conduct fatigue life predictions using methods such as SN curve analysis and cumulative damage models. These analyses estimate how many load cycles a structural component can withstand before fatigue cracks are likely to develop. Real operating conditions are also studied through duty cycle analysis, which evaluates the range and frequency of loads experienced during typical excavator operations. Based on these results, engineers optimize the structural design to improve durability. Modern excavator booms and arms are therefore designed with smooth load paths, optimized cross-sectional geometries, and reinforced high-stress regions. Weld joints are carefully designed and positioned to minimize stress concentrations, and advanced welding techniques are used to improve fatigue strength. In addition, manufacturers often use high-strength, low-alloy steels, which provide greater strength and fatigue resistance while maintaining reasonable weight. Through these advanced design practices and analyses, engineers ensure that excavator structures can safely withstand millions of loading cycles during their service life, allowing the machines to operate reliably even under harsh and demanding excavation conditions. Modern excavators increasingly rely on advanced electronic control systems to manage the complex dynamic interactions between hydraulics, mechanical structures, and external loads during operation. Traditional excavators depended largely on purely hydraulic control, where operator inputs directly regulated hydraulic valve openings. However, modern machines incorporate electro-hydraulic control architectures in which electronic sensors, controllers, and actuators work together to optimize machine performance in real time. A network of sensors continuously monitors the operating state of the excavator. These typically include hydraulic pressure sensors, flow sensors, cylinder position sensors, rotary encoders for swing motion, inertial measurement units, IMUs, engine speed sensors, and sometimes load estimation sensors integrated into the hydraulic system. Pressure sensors provide real-time information about the forces acting within the hydraulic cylinders, while position sensors track the motion of the boom, arm, and bucket. In some advanced systems, algorithms estimate bucket load by analyzing pressure differentials across hydraulic cylinders and the geometry of the linkage. All sensor signals are transmitted to one or more electronic control units, ECUs, which act as the central processing units of the machine. The ECU processes incoming data using control algorithms that determine the optimal hydraulic response for the current operating condition. Based on this analysis, the ECU regulates electro-hydraulic proportional valves which precisely control the flow and pressure of hydraulic oil delivered to cylinders and motors. By adjusting these parameters dynamically, the system ensures smooth motion, efficient energy usage, and improved controllability of the machine. One key function of modern control systems is power management. Excavators typically operate with limited engine power that must be distributed across multiple hydraulic functions simultaneously, such as boom lifting, arm movement, swing rotation, and travel motion. Electronic control systems coordinate the operation of variable displacement pumps, load-sensing valves, and flow-sharing systems to allocate hydraulic power efficiently. This prevents unnecessary energy losses and improves overall fuel efficiency. Advanced excavators also incorporate several dynamic control features designed to improve machine stability and operational precision. For example, boom bounce reduction systems minimize oscillations that occur when the boom is raised or lowered rapidly, especially when carrying heavy loads. These systems use sensor feedback and hydraulic damping control to counteract oscillatory motion in the boom structure. Similarly, swing control systems regulate the acceleration and deceleration of the upper structure during rotational motion. By controlling the hydraulic flow to the swing motor, these systems reduce sudden starts and stops that could otherwise generate large inertial forces. This not only improves operator comfort, but also reduces mechanical stress on components such as the slew bearing and swing gearbox. Another emerging capability is automated digging assistance, which uses sensor feedback and control algorithms to optimize excavation movements. These systems can automatically limit excessive bucket penetration, maintain optimal digging angles, and coordinate boom and arm motion to achieve efficient soil cutting. Some advanced excavators even incorporate semi-autonomous functions, where machine control algorithms assist the operator in performing repetitive tasks more efficiently. As excavators become more technologically advanced, electronic control systems are evolving toward integrated intelligent platforms that combine hydraulics, machine dynamics, and digital technologies. Future systems may incorporate machine learning algorithms, predictive maintenance models, and digital twin simulations to continuously optimize performance and detect potential component failures before they occur. Through these developments, dynamic control systems are becoming essential for improving productivity, energy efficiency, operational safety, and component durability. By actively managing forces, motion, and hydraulic power in real time, modern excavators can perform complex tasks more efficiently while minimizing mechanical stress and extending the overall service life of the machine.